So here we can see our very first example problem for free body diagrams and for calculating forces in cable structures. As always, the first thing for us to do is read the problem statement, and we are asked to draw the free body diagram for node A. Again, I'm nice enough to say that. Often you just have to solve it, but this actually leads you to the solution. Because afterwards you need to determine the tensile forces in cables AB and AC. And for this problem, we need to assume that the box actually has a volume of 3.5 cubic meters and is filled with water. And that is probably a good starting point for us to think of 3.5 cubic meters of water. And before I convert that into a force for us, let us remember that in this class, gravity is always given with 10 meters per second square and not 9.81 meters per second square. So this is different from your physics class that you used before, but this would be too precise for engineers, at least when we look at structures, because we're really pretending a precision that we don't have. And the 10 meters per second square is always on the conservative side. So if we use this, the 10 meters per second square, we remember that 1 liter of water is equal to 1 kilogram. And we also remember that 1 kilogram is really equal to 10 Newton, which comes from the fact that 1 Newton is really equal to 100 grams. That is very basic information that is covered in the very first lecture. However, you remember this, and therefore you can convert the 3.5 cubic meter of water into an acting force. So 1 cubic meter of water is really equal to 1,000 liters, right? And 1,000 liters times 1 kilogram is equal to 1,000 kilograms. So that means that we now have to multiply this by 10 to get to Newton, right? 1 kilogram is 10 newtons, so we're now going to multiply that. So therefore, that is equal to 10,000 Newton, which is really equal to 10 kilonewton. And the way engineers say that is that water really is 10 kilonewton per cubic meter. And so therefore we now understand the weight in this box is actually 35 kilonewton. But we could solve this problem with any force acting on it. That's not the point of this. This was just giving us an educational starting point here, and it could reinforce our understanding of the water concept. I encourage you to think about this also in the imperial system. Of course, in the SI system, 10 kilonewton per cubic meter, that's a very easy number and is very useful. And you will see many problems like this in this class that relate to water. So please also understand how this works in the imperial system. And maybe just for your notes, I can tell you that water in the imperial system is what? 62.4 pounds per foot cubed, right? So I'll tell you that much, but you need to know how to interact with that and how to use that. I just showed you how this works in the SI system. But again, this is not relevant to solving the problem. This just gave us an educational opportunity here to bring this in, how real engineers deal with this thing. Now it's our job to draw the free body diagram, including that force. So let's really cut or release node A, because that's what we're asked to solve for. And then we'll pull out our ruler, because every time we're asked to draw a free body diagram, we always use straight lines and we always do it with a ruler. So I have to perform properly. And then I take the sloped line from above and I draw that portion. Then I draw the other portion, and of course my weight hanging on the system, which is acting downwards with, as we said before, 35 kilonewton. Now, remember that we released and we really cut the system here as shown above. And right now the system would fall down, so I have to pull on the cables to bring it back into equilibrium. But the question is, by how much do we have to pull? Let me call this here AC and this here AB, because that's the naming of the cables. And again, here is node A. So now I can use that to draw my complete free body diagram, because remember, we need to include all the important components. Let's start with the actual horizontal and vertical components. So for example, the horizontal components for both of these and the vertical component. And the direction, that would otherwise lose a point if I don't do that. And then I need to give proper names. ABX, ABY, ACY, and ACX. Almost complete, but not yet. So we have to include our coordinate system, which I'm going to do right here, just randomly somewhere within the drawing. Of course, I could also do it right on top of it, or a lot of students choose to do it here, like to put the origin of the coordinate system right at node A. That's absolutely correct and acceptable, but I just choose to do it differently. And now we need to include our angles, and look at the picture here. The angle is really given with 76 to the horizontal, so that means here to the horizontal it's also 76. So I'm just going to use that. So because that's an enclosed angle here, so let's call this here 76 degrees. And then for the other one, I don't really need degrees because it is the 12, 5, 13 triangle, which always creates a right angle here if you have such lengths. We explained that before. And this again is an educational opportunity for us to practice this. But this now is my complete free body diagram, which now I can use my equilibrium equations and conditions to solve. So let's first write down what we're after. So I'm going to start solving f of x is equal to 0, all the sums of the forces, and I'm choosing to have everything positive to the right. So what that means is that we're looking at plus AB, so 0 is equal to plus ABX minus ACX. And that is everything that's acting in the horizontal or the x direction. So I can move on to my next equation, which is the sum of the forces in the y direction being equal to 0. And that is upwards positive. And therefore we have plus ABY plus ACY and minus 35 kilonewton. And that is technically Newton's third law, and it is already complete. However, we cannot solve this, and let me explain that to you. You see two equations with how many unknowns do you see? Exactly, we'll see 4, right? We have ABX, ABY, ACX, and ACY. So this cannot be solved. Some students try that, but obviously you remember this from your basic math classes that if you want to solve two equations, you need to do it with two unknowns. So what is the workaround here? I encourage you to think about that. The workaround really is that you can express ABY and ABX by one and the same unknown, which is AB. And I'm going to do that for you in a second. Likewise, AC can be used to express ACY and ACX. And so that's why I left some space here. Let's go ahead and do that. So I need, of course, access to my image here so that I can write 0 is equal to ABX. So what is ABX? ABX is really AB multiplied by 12 divided by 13, right? 12 over 13. And again, this is positive. And then I have to subtract my ACX, which is AC times the cosine of 76. So what I've done now is I expressed the horizontal component ABX in terms of the triangle here, and my ACX is expressed in terms of the cosine. And I'm going to do the same thing now for the vertical direction. So 0 is equal to plus AB times 5 divided by 13 plus AC times the sine of 76 minus 35 kilonewton. And those are now two equations with two unknowns. So check it out. I have AB as an unknown in this one and AB as an unknown in this one. And then likewise, I have AC and AC. So I can now go ahead and name them. Let's call this here equation 1 and this down here equation 2, which of course we all learned somewhere in high school or in other math classes how to solve two equations with two unknowns. But my general teaching philosophy is to show you at least once what I ask of you so that you can see where I'm coming from and where I want you to go with this. And also students just have different backgrounds in these classes, and I want to get all of them on the same page. So let's get started and rearrange first equation 1. So let's write that down. So rearrange which then turns out to be, let's say we'll solve it for AB. So AB is nothing else than AC cosine of 76 multiplied by 13 divided by 12. And that is my very first equation that is solved for AB now. That means that I now substitute that AB into my equation 2. So now I'm going to call 1 into 2. And so my equation then would really read that I have 35 kilonewton. I bring this to the other side, right? This is negative in this case, so I bring it over, is equal to AB, which is nothing else than AC times the cosine of 76 times 13 divided by 12. Now be careful, often students forget that this has to be multiplied by 5/13 now. So let's go ahead and do that. Multiplied by 5/13. And because AC is a common term now in this equation, I can just bracket that out. So that was that, plus AC times sine of 76. And that is actually the entire equation. So now all I have to do to solve for AC, so AC is really equal to 35 kilonewton divided by whatever we have here in the brackets. So that would be cosine 76 times 13 over 12 times 5/13, and of course the 13 actually cancels out, right? So we can cross those out, plus sine 76. And that will give you the final answer, which is nothing else than 32.68. And that of course is in kilonewton, and it is a result, so I better double underline it. And I, of course, also should provide my answer arrow, right? And now I have the answer to AC, which I can now substitute back into my original equation 1, which then will give me AB. So what I'm going to do next is I'm gonna take this value and substitute it back into here, which then means that I have 32.68 times cosine of 76 multiplied by 13/12, and that actually gives me a value of 8.564. And that is also in kilonewton. And it's a result. So my answer arrow needs to be provided. And last but not least, I can of course not just blindly trust these values. I am an engineer, so therefore I have to check my results. And how can I do that? I can of course check if these conditions are really true now. So let's go ahead and plug those values, for example, back into the original equation here. AB times 12/13 minus AC times cosine. So let's go ahead and do that, but I'm going to write that on the very bottom. So I'm going to call this a check. And my first one would be AB times 12/13. So AB would be 8.564 kilonewton multiplied by 12/13 minus AC, which is 32.68 kilonewton multiplied by the cosine of 76. And if I type that into my calculator, I end up with 0.0007 something, which effectively is 0, at least for engineers. We don't care about those precisions. In fact, that's why we're using 4 significant figures always. This is 0, and some of the imprecision actually stems from the fact that we used cosine and sine, and your calculator internally rounds these things. If we only were to use fraction, we actually would end up precisely with 0. We, of course, should still check our answer so that we definitely can get that A on the exam. So let's further check it, and let's run the other equation as well. So now I'm going to use the sum of the forces in the y direction, where I'm going to use 8.564 kilonewton. And I multiply this by 5/13. And in this case, I add the 32.68 kilonewton, which then is multiplied by the sine of 76. And that turns out to be 35.00 something, I think 3. But again, this is something we don't worry about. Therefore, we are correct. We now have properly solved the problem. We have even checked it. And if you would have done this check on an exam, which only half the students always do, then you would know for sure that you are correct. So let's take a look at this picture again, at the overview. And let's understand that we solved the free body diagram problem. We used then the free body diagram and set up our equations. We moved from equations with 4 unknowns, right? So we had 2 equations with 4 unknowns that we then expressed with the same 2 unknowns, A, B, and AC, so that we have 2 equations with 2 unknowns that we then can solve by using substitution methods that I showed to you down here. And I just had to rearrange it to end up at my answer. And ultimately, I want to run a check. That's why we're engineers. We always check it. Nobody will tell us if it's right or wrong. We have to determine that ourselves. So I check my answer and I validated that this is correct. I believe that concludes this problem, and we can conceptually talk about the one on the following page. So here you see another example problem where you have to draw the free body diagram for node B in this case, right? So node B is given to you here, and we have 2 sub-problems here. I want to ask you to solve this for 2 different weights. For the first case, I would like you to think of it as the traffic light with a mass of 150 grams, which of course is way too little for a real traffic light, but it is giving us an opportunity to practice our engineering understanding if then in the second problem we do it for 250 grams. And I don't have to solve this problem for you because it's very similar to what you've seen before. just that here now you're dealing with two angles. I will, however, give you the answer, and the answer for at least the first problem would be that the force in AB, so let's call that FAB for 150 grams, would be equal to 1.272 Newton. And then FAC for 150 grams would give you a value of 0.531. 0.531. So that gives you a chance to practice this. And I really encourage you to do that so that you can use your knowledge that you developed in this sub-problem number 1 to come up with a smart way to quickly answer problem 2. So my best advice to you here is work smarter, not harder, and think deeply about the answers that led you here, or think deeply about the process that led you to these answers, so that you can then find the most quickest way to arrive at the solution for problem number 2. And of course, I don't want to give this away here. I want to encourage you to really think about this. So while I think this is very important, I don't want to tell you how it's done, because it's a very important revelation in your engineering education. So go ahead and calculate that. And if you don't find an easy way, if you think it's just as complicated as you solved for this, then I will encourage you to also find a solution for, let's say, FAB due to 200 grams, and also for FAC due to 200 grams. And then look at the ratio between the two. So compare this one to this one, and compare this one to that one. That should give you a very important engineering tool if you really understand how those results relate to each other. And that is, I think, everything I want to tell you here to keep your curiosity up and to also encourage you to solve this problem on your own. With that said, we have done enough examples for the free body diagrams and the equilibrium conditions and equilibrium equations. So let's move on to our homework problems.